Hi everyone, we are going to start with limits and properties of limits today. You can read all this stuff. Okay, I know it looks like a lot of math notation and some of this might be new, but you can read this if you have questions. You can ask me about this in class. Just keep in mind, I guess the important parts are up here. It tells you that the answer or the limit of my function as x approaches c is this capital L. The limit of g of x as x approaches c is this capital M. Okay, so these are like the solutions, okay, or the answers to our limit question, and we use them here. Okay, so you can add, you can subtract, you can multiply quotient, constants, and then such and such. Okay, so you can read through this. If you have questions on them, you can ask me, but I want to jump straight into the application. So first thing we're going to do is we have some stuff here. They gave us no actual functions, just a bunch of letters, but they did tell us that the limit of f of x as x approaches a is 2, and then the limit of g of x as x approaches a is 3. Okay, so notice that these are the same number. Okay, and then it wants us to find the limit. Well, first they just want us to find the limit as x approaches a of 5 times g of x. Well, this is going to be the exact same thing as if I just brought the 5 out. 5 times the limit as x approaches a of g of x. It's going to be the same thing. Sometimes it's easier if you bring it out, sometimes it's easier if you bring it in, depends on the problem. Okay, but so long as you know that you can take this constant in or out of your limit, because constants don't change. Well, I know the answer to this. Okay, the limit as x approaches a of g of x is 3. 5 times 3 is usually 15. Okay, couple special trig limits. Okay, a couple special trig limits. We have the limit as theta approaches 0 of sine of theta over theta. This is going to be 1. Okay, and then we have the limit as theta approaches 0, 1 minus cosine theta over theta. This is going to be 0. Okay, now keep in mind, if you just plugged in 0 for theta, you get 0 over 0 here. Okay, same thing here, you get 0 over 0. That's, again, indeterminate form. Okay, so if you watch the pre-cal review video, then we went over that. It's indeterminate form, and that just tells you that you have something else that you have to do. Now, we don't really have a strategy for this yet. Okay, solving indeterminate form for this, we don't have a strategy for that yet. We will learn that later. Okay, but for now, what you need to know is this situation right here. Okay, now specifically with this limit, because it's very common. Okay, all that needs to be happening with this is this right here and this right here just need to match. So we could have sine of, I don't know, 2 theta over 2 theta, and so long as this and this match, it's going to be 1. Similarly, say we have a different variable, x approaches 0 this time, okay, and we have sine of 4 pi x over 4 pi x. Okay, again, so long as these match, my limit is going to be 1. Okay, that's the important thing to note. But what if they don't match? Well, here I have a 5x, I have a 4x. Okay, it would be really easy if this was a 5x. It would be really easy. That's actually my goal, is to get this to have a 5x. Really, I'm going to force this to have a 5x in a way. So remember your limit rules. Okay, what we did, that very first problem that we did, we can take out constants. So I can rewrite this. Okay, so imagine this was our problem instead. Okay, so all I did was took that 1/4 out. Well, now it's very clearly a constant. Okay, I see that this is just a number. It's separate from here. It's just a number. It's multiplying. Well, I can take this out. Let's take that out. Okay, I don't even want to deal with it. I don't want to see it inside my limit. Well, okay, that helps, but that doesn't actually solve my problem. I still need a 5 here. Well, we can introduce a 5. Remember, if you can take constants out, you can put constants in. So I need a 5 here, but you can't just introduce a 5, right? Like, that just breaks the rules. You can't just multiply this by 1/5. You can multiply it by 1, though. So I'm going to multiply this by 5 over 5. All right, what do I get? Well, you know what? This 5, up here, this numerator, I don't want it inside my limit, so I'm going to keep that out. This 5 I do want inside my limit, so I'm going to bring that in. Okay, now, it's very important. I did not actually change anything. Okay, this 5 and this 5, I could still cancel out at any time. This 1/4 I could bring inside my limit whenever I want. I would have the exact same thing that I started with. That's very important. Make sure anything you do, you could do the reverse, you get the same thing back. Okay, that means you didn't break any rules. Now I have what I want. Okay, I have a 5x here, I have a 5x here. I know that this limit is going to be 1. So my answer is just 5/4. Okay, right here. This looks a little more complicated. Well, you know what? Let's just use, this isn't even a limit thing. Let's just split this fraction. Okay, so I have 2x over x plus sine of x over x. And I'm just going to make these brackets clear that it's all inside of this limit. Okay, so I don't let anyone confuse what I'm trying to do. Well, I cancel this if I wanted to, but you don't have to. And so I have the limit as x approaches 0 of 2 plus sine of x over x. Well, remember, if you have a plus sign here, you can split this into two different limits. Okay, so that's kind of using your sum rule. So this is going to be the same thing as the limit as x approaches 0 of 2x over x, which is just 2, plus the limit as x approaches 0 of sine of x over x. Well, the limit of 2, there's no x's here, so that's just a constant function. That's always going to be 2, so the limit's 2. Here, this is my special trig limit, and I get 3. Okay, one more thing to cover is called squeeze theorem. And squeeze theorem can be a little weird just because you haven't dealt with a lot of things like this. It seems kind of obvious. Okay, a lot of math theorems seem kind of obvious, but it's important to have a mathematical way to prove something. Okay, that follows like a logical progression. Something like facts that you can back up your argument with. Okay, so that's exactly what we're doing here. Again, it might seem obvious, but it is important to have like a mathematical basis for your argument when you're doing a proof. So this is squeeze theorem, and so if we have some functions, okay, I have an h of x, f of x, g of x. F of x is between h of x and g of x. Okay, for all x in an open interval containing c, you don't really have to worry about this stuff. And if my limit of h of x equals L, my limit of g of x equals L as x approaches c, then my limit of f of x as x approaches c equals L. Okay, so if you think about it, it might be kind of obvious, right? Like, if this approaches a number and this approaches the same number and this is between them, then it should approach the same number, right? So if you don't understand what I'm saying, let's look at this graphically. Okay, so what I am telling you is if we have, say my h of x is like some constant. Okay, that doesn't look like a constant, but that's what I meant. Okay, so this is my h of x. And say my g of x is something else. Okay, this is my g of x. You know what, let's make that lowercase. Right, and this is my point C. All right, notice how g of x is here, h of x is here, g of x is greater than or equal to h of x at every point. Okay, it's equal here, but it's greater than at every other point. I have an f of x that fits between these. It's sandwiched between these functions. Now, if you're going to make this function continuous, meaning you draw it without picking up your pencil, there's no, and no, I mean, it has to be between these. There's no way that you could make it go over here or over here. So say, I don't know, this is my function. It could look like anything. Well, it's getting squeezed. It's getting squeezed in between them here, and then it emerges from the other side and does whatever. Okay, but what's important is at this point C, it's squeezed between my h of x and my g of x. So this is my f of x function. Okay, it's squeezed between my h of x and my g of x function at C. So I don't know what's happening everywhere else. I don't need to know what's happening everywhere else. All I care about is what's happening at C. So let's look at a problem. Okay, so I have 2 is less than or equal to f of x less than or equal to x squared plus 2, which is kind of what I did here. For all x, it wants me to find the actual limit of f of x. Okay, I don't know what f of x is. I don't care what f of x is because I can use my squeeze theorem. So in an inequality, you've worked with inequalities before. If you do something to one thing, you have to do it to all of them. So I'm going to evaluate the limit. Okay, I'm going to evaluate the limit as x approaches 0 of all of my functions here. So the limit of 2, limit as x approaches 0 of f of x, and same thing here. Okay, so this is exactly what I'm trying to figure out. Now, again, the limit of a constant is just going to be that constant. Again, this is what I am seeking to find. And if I plug 0 into my limit here, 0 plus 2 is 2. Hey, look at that. So just like what my theorem said here, okay, so the limit of whatever equals L, the limit of whatever equals L. Okay, so my limit equals 2, my limit equals 2. So in this case, 2 and L, are the same thing. So I know the limit as x approaches 0 of f of x has to be greater than or equal to 2 and less than or equal to 2 at the same time. It has to be between 2 and 2. So if it's between 2 and 2, it's probably 2. So I can say therefore, so 3 dots means therefore, by squeeze theorem, the limit as x approaches 0 of f of x equals 2. Alright, that is it for this video. See y'all later.